Hi everyone. So like I said, my name is Onyekachukwu Ojumah. You can find me on LinkedIn there, so connect with me, I'll connect with you too. So today I'm going to be talking about a very distinct topic. I think the first time I came across additive manufacturing, it was after my MSc. I came back to school to just walk around, and I saw a group of people, BSc holders, they were printing things like necklace things, and then they design it for you, and you choose your design, they change the mode, they print it out, and then you wear. And I was so curious, what are these people doing? What's going on? I come from computing background. I've never seen, when I think of manufacturing, I think of factories. So I spoke to the young man, and he was like, oh, this is what it's about, 3D printing. I was like, okay, wow. So I didn't get a lecturer that could relate with both tech and additive manufacturing. But fortunately, I was able to meet a new lecturer that came in and was talking about, he does deep learning, machine learning for manufacturing. So I told him, oh, have you heard of additive manufacturing? And he was like, yeah, that's a very cool project. So I was like, I'm interested in that. I want to know more about it. So he brought me in for PhD. I've not started, but yeah, we're still in conversation about that. So it's from manufacturing background here. Oh, wow. So I know more, yeah. Oh, I'll pretend not to see. I'm just kidding. So additive manufacturing is all about 3D printing. It's the ability to use 3D printers to build parts layer by layer to enable us to form complex parts, complex shapes. So sometimes I think the whole idea of why additive manufacturing came into play is that there are some parts that are very difficult to do it using traditional method. They have weird shapes. They have an high level of precision is required, especially when it comes to the aeronautic space. So additive manufacturing allows manufacturers to be able to use materials. This could be metal, plastic in powder form, and layer by layer, they're able to mold these parts just like you're printing. But when we were having a conversation as to where does additive manufacturing relate to tech, my supervisor said porosity. That one of the reasons why many manufacturing companies are struggling with adopting additive manufacturing in their process or in their process of making parts is because of porosity. Some of the materials being used in additive manufacturing, some of the metal powders being used, tend to be they tend to easily have issues with porosity. So what is porosity? Sometimes when you take a block, I don't know if we've ever experienced like a block of metal or a block of something, and then you could see those tiny hairs in there. With your physical eye, there are pores in those objects, they could be plastic, but when you look at it well, you can, sometimes when you even get a plastic and you pour water, you could just see a tiny leak somewhere. Sometimes the pores is big, sometimes it's small. The problem with this porosity is that it affects quality. So when you print out a part, no matter the material you use, and the porosity, that is, imagine you print out these objects, and 70% of this object is made up of tiny hair. How sustainable will it be? Or imagine if you're in a bottling company manufacturing bottles, and then you have pores in those bottles. It's easy for microorganisms to be able to live in those pores, and then you then put drinking something that goes into the system, into those bottles. Before you know, you're getting a lawsuit. So measuring porosity or dictating porosity in any object is very important. It allows us to know what parts or what parts should we accept, what parts should we reject. Another reason why we measure porosity is so that because the 3D printers have settings and different the way you arrange those settings, which I'll talk about in the next slide, affects the quality of the material. So how do you know the optimum settings for your 3D printer to get the best, to get the product that will have the least porosity? So this is where porosity detection comes into place. And also for audits, being able to take track of the printing settings that give you the best product and the printing setting that gives you the worst products. This will prevent people from using that setting and causing issues for themselves. These are the different settings that affect your 3D printer and the results. But what does this have to do with us in tech? In tech, there's something we call design of experiments, whereby we conduct experiments by changing the values and fine-tuning the values of things to see how they affect the outputs. This is where we come in. These different settings is what we use to conduct our input-output experiment for our machine learning models, our deep learning models. Before the whole conversation as to where tech can come into helping additive manufacturing, there's something that they do which is called dyeing, whereby when they produce an object, they pass dye into it that forms kind of like a gooey shape. When they bring it out with their physical eye, they could see where the space is. Then there were accuracy problems. So they brought about X-ray, whereby when they produce a part, they scan it. I remember I was speaking to Claire, and I was talking about shooting X-ray. I'm not there. You can't find me there, but I want you to write the code. But that's actually part of the fun in additive manufacturing. So they scan, when you produce a part, you scan it like front, the back, scan it. And with the X-ray, with the CT scan, you're able to see where the pore is. So before now, experts were the ones doing it. They would just look at it and say, oh, you have a lot of pores at this angle of the parts, a lot of pores at this angle, and based on my rough calculation, 85% of this parts is made up of pores. We should reject it. That's just physical examination. But then experts came and they had concerns. How accurate is our physical eyes in seeing pores compared to a machine being able to see these pores for us? And yeah, if you look at the image, I don't know if you can still hear me, but this is just a block of metal which has been printed. And when you scan it, you're able to see dots, which tells you where the holes are. So when you want to see it clearly by removing every other, just to focus on the pores. So this is the diameter. The ones that are pink are the ones that are really, really large. You see them more at this side. So it means you have like really large pores there and this side. And then the least are like the purple and all of that. But that's just to your naked eye. And how accurate, what are the ones that you can't capture with your naked eye? This is where deep learning comes into play. So who has worked with segmentation, model, image classification? Anyone? Yeah? Yeah, this is our strength. So the conversation was that instead of having experts look at these CT scans, how about we build deep learning models to look at these scans? This is because we know that they will detect faster, and we can automate the process. Once we've gotten the model up and running, we just from scanning straight to detection. There's no wasting of time, and production can happen quickly. Correction and improvement can happen quickly. So if you look at it here, you have your CT scan, your CT slides, and this will be what normally we'll call the pore. Yeah, the pore. And then you pass it through your segmentation model. Then you get your segmentation marks, which is sometimes captures pores that our naked eyes can't see. But how do we get this data? That has been one of the conversations. There's no automatic way as such of getting this data. We're still going to have to deal with the manual process. So the first conversation has been, we physically go collaborate with the manufacturing manufacturing organizations, or like when you look at my university now, we that are in computing, we have to collaborate with those in manufacturing and material science to have them print out these parts. So they print out the part, they tell us the printing settings they use, the material they use in printing these parts. They scan it and they give us the slide, the data sets. Another way we can do is to have virtual CT scan data. Has anyone heard about software simulation to getting data? Yeah. So we're saying, is it possible for us to simulate the printing out an object, simulate the object having pores in them, and then simulate a kind of an X-ray scanning? That would take the fun out for clay, but that's all right. We just simulate everything. But the problem with simulating everything is that it takes away reality. How are we sure that what we are simulating is close to reality? So there's been, if you look at a couple of research papers lately on additive manufacturing, there's been a call for an hybrid model whereby we combine both reality and simulation to have a much more enriched data. So one of the challenges you face, or we do face in data acquisition, is annotation quality. The truth is that there are only two ways right now, based on research, that we can annotate this data. Either someone still comes back, that physical method we are trying to avoid, someone comes back and still physically annotates this data to be able to train the model on what the pore look like. Or we have softwares that, based on threshold, are able to say, if you look at this image, if you have a threshold working for this image, we can set a threshold that says that any part that is of this pixel value, which is the dark part, is the background. That's the material. And any part of this pixel value is the image, is the pore, which is the region of interest, right? Which is the region of interest. The thing about that is that in both ways, we still will not capture all pores, but at least we'll be able to give the deep learning model an idea of what pores should look like in a CT scan. The next thing we move to data pre-processing. Usually when CT scan comes, if those of us that have worked with CT scan, we know that most of them come in 3D formats. But not every model in deep learning is equipped to work with 3D scan. So then we have to convert them to 2D scan. Then noise reduction. Is anyone familiar with noise on image? Yeah. So when it comes to noise reduction, how do we know the right filter to use? Sometimes you use some filter and they end up removing information. And sometimes you use some filter and they don't take the noise away. When we had this conversation, I told them the only way you can know is to keep experimenting. As machine learning engineers, our job, we will keep on experimenting. We'll keep on trying different things to know what works, and then we publish it and say, oh, this is what I think works for now. So that, okay, that's okay. Yeah, okay.
What are the main sources of noise? What's the most important source of noise?
Okay, so for additive manufacturing X-ray scan, sometimes during the adding process, it introduces noise to during the adding process, noise gets introduced to the CT scan. I'm trying to look at other examples. Sometimes it's just the way the image is printed if it comes to normal images. Noise are just things that, they are not the material, they are not the pores we are looking for. They're just interruptions. So we just filter them out to make the image more clearer. Or does anyone want to give a better explanation of what noise is? Noise.
Perhaps one could define it as the things that aren't the signal, but they are often composed of other real things. And that's why it's interesting to know what the source of the noise is, because it's usually a number of different things, but then typically be one or two that dominate. Which might just be things like the fact that your instrument's on a floor that vibrates with passing traffic. That would be an example of noise.
Interesting.
You get noise just because your electronics are not allowed to exist.
Yeah, that noise because electrons are actually
Okay, so we get rid of the noise, experimenting with different filters, and then intensity normalization. So when you look at a data set that contains CT scan, you tend to realize that some are brighter, some are darker, and all of those things. If we send it through to the model like that, the model can decide to focus on just the brighter images and just leave the. So what we want to do is to bring them at an equal level through normalization. So cropping and then resizing, remove the irrelevant parts so the model can focus on the region of interest. And then data augmentation. Who doesn't know about data augmentation? Yeah, we're good. So I remember I mentioned data annotation, like being able to label where the pores are to enable because that would be the output training data. So like I mentioned before, manual, an expert sits down and starts drawing. That's very expensive, time-consuming. Semi-automated thresholding, but an expert will have to correct it because sometimes it can be wrong. But if you use simulated data and you are the one that actually simulated the pores into it, you know where the pores are. So and then the software also knows where the pores are. That's easier for you to be able to, to annotate. So depending on how you want to do it, you could just mix, you could have like simulated data, you already know where the pores are, and then you annotate it. Then we have the model training. So when we're having this conversation, and at the early stage of my career, I always misclassify classification model with segmentation model. So just in case anyone was like me or is like me, I don't know which one, but just in case you can't tell the difference. So when it comes to classification models for images, we're looking at the image as a whole, and we're trying to identify it or recognize it. When it comes to segmentation models, we're segmenting the model into pixels to determine if this pixel contains what we are looking for. So breaking the model, we're not recognizing the model, oh, this is an X-ray. We just want to know, does this part contain, does this part contain, does this part contain? And as a whole, what's the percentage of this part that contains what we are looking for as a whole? So you can play around with optimizers. I did the research using Adam X. You can play around with that. And then what we are to check if there is no overfitting, which all of us know, we look at our validation and our test loss function. So who has heard of transfer learning? Don't worry, we're almost rounding up. Manufacturing can be a very long, dragging topic, but it's very interesting when you're doing it physically. Who has heard of transfer learning? Do you want to help us? Transfer learning? We should have all heard of transfer learning. Yeah, please go ahead.
Okay, so it's using the knowledge of bigger model to train something smaller and easier to execute.
Thank you so much. Very simple. Do you have addition, something different? Yeah. So that's it. Part of the conversations that is happening within my department, my department, is that how can we use transfer learning to build more powerful models to be able to recognize pores? Even if we do not annotate our data so well, this machine is able to still recognize the things that we did not pay attention, like the very tiny pore that is like a dot that we did not pay attention to. The machine is still able to recognize it. So what we can do is that a typical segmentation model is made up of encoder, decoder, the final convolutional layer, and then the output mask. So what we do is replace the encoder with a bigger model that has been trained to recognize images, so that when it comes to extracting the features, it does it quicker. And then the rest of the model is still either your VNet or your ZNet or whatever it is. So you can play around with the different transfer learning models, like the pre-trained CNN models, Efficient nets is what I used for my master's dissertation. It was very interesting to use. But the problem with these models, well, we'll get there. So these different ways we can measure results. Don't worry, I'm almost running off. Different ways we can measure results. So we can see, okay, in terms of what it predicted and what the actual, because the output will be in range, like 0 will be no pause. So for each pixel, it only takes an image. For each pixel, 0, no pause, 1 pause, 0. So before now, it forms a range of numbers. So you compare what the actual number should be and how far apart it is from the predicted number. So like we said before, if AI comes into play, it's easier, it's faster, and the thing about when you build these deep learning models is that most companies have what we call inspection systems, whereby if you notice to reject this, accept this, reject this. So now we can make it much more intelligent by adding this system to inspect the products. It also saves costs because you don't have to print out a large batch before realizing that there's something wrong. From a small batch, you can quickly realize and make that adjustment. Like I talked about the limitation, transfer learning models are very expensive. I remember running I did something about lung cancer, and I used CT scan to predict if there's a lung cancer or something like that. And I had to run some of these models for like 6 hours, 7 hours. My laptop was making noise. But that's it. They are heavy when you use computational models. So how do we make them smaller, easier, and faster, and all of that? And sometimes I build a model that works really well for plastic. And then when the company decides to start building with metals, it doesn't work really well for metals. So the future work is experimenting, like I said, with different materials and processes, then combining real data with synthetic data. And then sometimes there's an option of, what if we don't even annotate this data that we want to train the model with? What if we just give it and then using LLM, ask it to bring out the pause? Do you get? Or something like that, just something that does not involve us touching the data. We just print out the CT scan and then it tells us where the pause are and what to do about it. So these are the resources. You can check them out if you're very interested in manufacturing and tech. You should be, to be honest. It's very interesting. Don't mind the way I presented it today. It is very, very interesting. It's very fun because you get to do something physical and not just always be behind the screen. You do something physical, you play with it, and then you say, yeah, this is the results. So I remain Onyekachukwu. Ojumah, you can find me here. Do we have any question?